Okay, let's continue ZEUS training with section 9, Miscellaneous Input. So these are the miscellaneous bulk data cards that we have in ZEUS that are referred to by many of the other bulk data cards. We've mentioned AEFACT several times. That allows you to specify a list of real numbers. The Cord2R defines a rectangular coordinate system. LOADMOD, that's important. That allows you to define component loads. Output 4 will output data onto an output 4 data file. The PAN-LST cards define sets of aerodynamic boxes. We've mentioned the PARAM. That allows you to alter global parameters in ZEUS. And then the set1 defines a list of identification numbers, most often used for grid IDs. Okay, so the AEFACT allows you to list a set of real numbers. So we have an ID number and then an open-ended input with as many real numbers as you would like. Most often you'll use this referred to by ZEUS or gap cards, where you'll list out something in terms of percentage, where your values will range from 0 to 100, for example. This AEFACT card, we just have these three real numbers, 0.3, 0.7, and 1.0. Remember that real numbers in the ZEUS input must always contain a decimal point, whereas integers must not contain a decimal point. So in the AEFACT card, every field other than the ID must contain a decimal point. Next we have the PAN-LST1 card, which defines a set of aerodynamic boxes. And we do this by specifying two corner boxes. So in this example, we have a ZEUS with ID 111, and then end span is 5, end chord is 4. So you can see the resulting ID numbers for the aerodynamic boxes here. So with the PAN-LST1, you specify two box IDs. The first box ID is the inboard leading edge box, which in this example is 111, and then the second box ID is the outboard or the right-hand side trailing edge box, in this case 118. So when you specify 111, 118, it selects these 6 boxes as being part of the group of boxes. So 111, 112, 114, 115, 117, and 118. The PAN-LST1 is very convenient for defining control surfaces. So if this is some sort of leading edge control surface, you can see how that works. If you wanted to define a trailing edge control surface consisting of just boxes 119 and 122, then box 1 would be 119 because that's the leading leftmost box, and then 122 would be your second ID because that's the trailing rightmost box. So we have the ID number of the PAN-LST, then macro ID is the ID number of the ZEUS, and then box 1 and box 2 are what we just described. So this is referred to by the spline, attach, which is another spline method, LOADMOD for component loads, CPFACT, or the AESRV. Next we have the PAN-LST2. This one you just list out the IDs of the boxes. So it works similarly to the set1 card. So once again we have the macro ID, and then we have the box IDs. And we do have the through option available. So field 5 can be through. So in this case here, we're listing boxes 1, 2, and 3. In this case, we just have boxes 104 and 25. The macro ID is used to define the spline plane for the infinite plane span method, the spline 1. So if you're referring to it by the spline 1, the macro ID is required. Otherwise, it looks like the macro ID is not required. Next, we have the PAN-LST3, which refers to entire components by their label. So we have the ID number, and then we have the labels. And so this is how we can have multiple components all listed by one PAN-LST card. So in this example, we just want to refer to the entire wing. Remember, the C 7 and body 7 have a label field, and that's the label that this is referring to. Now, it is allowed to have multiple PAN-LST cards with the same ID. So if we go back to the picture of our wing here, let's say we have the PAN-LST1 to pick up these 6 boxes, and then we use a PAN-LST2 box to pick up box 120, and we want these 7 boxes to be selected for the spline. That is fine. We would have the PAN-LST1 with ID, for example, 200, and then we'd have the PAN-LST2 with ID 200, and ZEUS will combine those two PAN-LST definitions, so we have that one box set with ID 200. Next, we have the set1 card to define a list of integers. So we have the ID number, and then we have an open-ended input list of integers. The set1 supports the through option, so we can have 5 through 10 to list out the numbers 5, 6, 7, 8, 9, 10. And then we also have where you can just explicitly list out each number, for example, 110 and 120. These two cannot be combined. If you do make use of the through option, you're only allowed to have this one set of numbers, 5 through 10. You cannot then have additional numbers out here. So this card right here is invalid. It's not allowed. Next, we have the Chord2R card to define a rectangular coordinate system by specifying the 3 coordinate points. So the first point, point A, defines the origin of this coordinate system. The second point, point B, defines a point along the z-axis. So this vector AB defines the z-axis. And then point C here defines the xz plane along with points A and B. So if we take the cross product of vector AB and AC, you can see that we get the y-axis, and then once we have the z-axis and y-axis, we can find the x-axis here. The RID field is not used in ZEUS, so unlike Nastran, you cannot have Chord2R cards reference other Chord2R cards. The Chord2R card here is always in the basic coordinate system. Next, we have the LOADMOD card to define a load mode of a set of structural grid points for computing component loads. So we have an ID number for the LOADMOD card. Next, we have the label field, which defines the type of the load mode. So it must be one of X shear, Y shear, and Z shear, or X moment, Y moment, or Z moment. So the shear options are the shear force along the X-axis, Y-axis, or Z-axis of coordinate system CP. And then X moment, Y moment, Z moment are the moment forces along the X, Y, or Z axis of the coordinate system CP. And then we have field CP, which refers to a Chord2R card to define the coordinate system. And next we have set K and set G. Set K refers to the PAN-LST1, PAN-LST2, and or PAN-LST3 bulk data cards, which list out the aerodynamic box IDs for computing aerodynamic forces. And then set G refers to set 1 and or set add bulk data cards to define the structural grid points for computing the inertial forces. CP can be 0, in which case the basic coordinate system is used, but most often you will make use of the CP field. Remember, for the H to F option, where you have a half span structure model but a full span aerodynamic model, the grid IDs on the left hand side are negative. But here, set G in the LOADMOD card can be a negative integer. So in this case, the sign of all of the structure grid IDs in the set 1 or set add cards are reversed. So this way you can avoid having 2 different set 1 cards, one for the right hand side, one for the left hand side. You can just reuse the same set 1 card that defines the grids on the right hand side, and then use the negative integer in the LOADMOD card to switch over to the left hand side grids. So that's kind of a nice convenience. Next, we have the output for card to export a matrix data entity. So we have mat name, which is the name of the matrix on the ZEUS runtime database, which will be exported. So in this example, UGTKG is the spline matrix. The file name is just the name of the file. So usually I just have the name of the matrix and then append.dat to make it easy. And then form defines the format of the file. So it can be either format, format 23, or unform. For format, we output with 10 digits of precision. For format 23, we output with 17 digits of precision. And then for unform, we create a binary output for file. And these are some of the matrix names that we have in ZEUS that you can export. So we have the spline matrix, we have the plot spline matrix, the force spline matrix, we have the phi, the modal matrices, MHH, KHH. Phi K is the modal matrix on the aerodynamic boxes. We have MGH. And then next we have the PARAM bulk data card to alter global parameters of the ZEUS solver. So we have the parameter name and then the value. And the value can be either integer, real number, or character depending on the parameter. So first we have alpha. Let's see, this is alpha reference. So this is the pitch amplitude in degrees as a small perturbation to extract the aerodynamic stability derivatives for the trim analysis, and as the oscillation amplitude to extract the frequency domain aerodynamic forces for flutter analysis. Next we have body CPX, default 0, so this is the flag. If the value is 1, then ZEUS will apply a correction scheme to obtain the pressure coefficients from the rectangular box to the actual surface of the body. Next we have Chimera. Chimera is the most often one that you will use. So the default for Chimera is 1. And this is used in the overset mesh. So this is a factor to increase the allocated memory used in the overset hole cutting computation. So before ZEUS generates the overset mesh, it has to assume some amount of memory that it will need in calculating the overset hole cutting computation. It can't really, there's not a good way for it to guess how much memory it needs beforehand. So a value of 1 here is just the default guess. For some models, you'll need to increase the value of Chimera. So this will increase the memory usage by ZEUS, but it is required to allow ZEUS to get through the hole cutting module in the mesh generator. So if the default 1 doesn't work, I'd recommend increasing it to 5 or 10. I think the highest I've ever had to set Chimera is 15 or 20. So basically the first try, just try going up to 5, and try 10, 15, and so forth. Next is the damping. This is the damping ratio used in the composite sinusoidal excitation technique. Next we have the follower force option. So the default is 1. The follower force is enabled. If the follower force option is enabled, then the aerodynamic forces are applied on the instantaneous deformed shape of the aerodynamic surface mesh at every time step, but you can disable that by setting follower to 0. Free component, we just discussed that a few slides back. That's a character string, either yes or no. Next is iBlank, which is an integer. The default, let's see, if the value is, okay, so this one's confusing. If you do not have the iBlank parameter present in the input deck, then this file is not generated. However, if you have iBlank present and then you specify 0, ZEUS will generate a plot3D file to store the cell center points of the overset mesh, including the iBlank array. If the value is not 0, then it refers to an ext file card to define the file name. So for 0, the file name is conp3d mod.dat. Otherwise, you can define your own file name by using the ext file card. The vast majority of the time, you don't have to worry about this, but if you're trying to troubleshoot the overset mesh and trying to determine which blocks are contributing their flow solution to other blocks, you may be able to use the iBlank option to see the full volume mesh to see which cells are donor cells and which cells are receiver cells. But most often you don't need to worry about that. Next we have ISXK. So for a value of 1, which is the default, ZEUS computes the frequency domain, generalized aerodynamic forces at k equals 0 using the quasi-static computation. For a value of 2, it computes the frequency domain, generalized aerodynamic forces at k equals 0 using the composite sinusoidal excitation. Next we have the LFAC run, which is a flag for the maneuver loads. So the default here is a normal maneuver loads run. Now for the mloads analysis, if the code stops accidentally and no output file is generated from that specified in the MLD print card, then you can use a fake run to recover the output file generated by the MLD print card with the help of the generalized coordinate time history data stored in the files qshistory.dat. So if you turn on the LFAC run to 1, ZEUS won't actually redo the maneuver loads analysis. It will just read your history file here to generate the MLD print card. Next we have LYSLP, which is the Y-slope effect. So the Y-slope effect is ignored on horizontal surfaces with a sweep angle larger than Ly slope degrees, where the default is 60. So if our slope is greater than 60 degrees, then the slope effect is ignored. Next we have max trim, which is the maximum number of iterations in the trim analysis, and the default is 3. So if for some reason, or if you want to run faster trim analysis and you don't care about getting as converged of a solution, you could decrease max trim. Or if you want to allow ZEUS to run more trim iterations, you could increase max trim. Usually ZEUS will converge in 2 or 3 trim iterations. Next we have N2CYC. This is the number of cycles for the sinusoidal excitation to compute the harmonic response for generating the frequency domain generalized aerodynamic forces in the flutter module. So the default is 2. So when we use the sinusoidal excitation technique to compute the generalized aerodynamic forces in the flutter module, the ZEUS solver will go through two cycles. Now only the last cycle is used when we perform the inverse Fourier transform to get back the frequency domain gaffs. So if you want to just run one cycle, you could change this to 1. However, that's not recommended because the very first cycle may have some initial transient response that you don't want. So the default is 2 to get rid of all those unwanted transients on the first cycle, and then by the second cycle, we're assuming that we're fully within that just the purely harmonic response. So if you want a more accurate result, you could try increasing this so ZEUS runs more cycles, but however, the Fourier transform is always only performed on the last cycle. But 2 is adequate, so that's the default. Next, we have ST relax. This is a real number. It's a relaxation factor for the static aeroelastic trim analysis. Now, during the iteration between the aerodynamic and the structure coupling procedure, the modal coordinate solution, which is called XS, is updated by this equation to scale the current modal coordinate solution with that of the previous iteration, XN. And so this ST relax is this quantity here. Now, usually if the static aeroelastic analysis fails to converge, using a larger ST relax can improve the convergence. Next, we have a stiffer option to artificially increase the stiffness of the structure. So the default is 1. The square of stiffer is multiplied to the generalized stiffness matrix to create a stiffer structure, and this is only used in the trim analysis. So you can do this to run a trim analysis but on the rigid structure. So if you put in a very large value for stiffer, for example, 1,000, so you're increasing the generalized stiffness by a factor of 1,000, essentially you're turning the structure into a rigid structure. So then if you do a trim analysis, there are no static or elastic effects, you're just performing the trim on the rigid structure. Next we have the trim reduce. The trim analysis first computes the mean flow solution for the trim variable thick cam using the trim step number of pseudo time steps, where trim step is specified in the MK param card. And then, based on the mean flow solution as the initial flow condition, the trim analysis computes the aerodynamic stability derivatives for the other trim variables, such as angle of attack, control surface, etc. On those computations, the number of pseudo time steps is reduced by a factor of trim reduce. So the total number of steps is just trim step divided by trim reduce. Next we have trim CNV. At each trim iteration, if all of the trim variables are smaller than the trim convergence times the respective value at the first trim iteration, then the trim iteration is converged. So the default is 3%. So if you want ZEUS to run longer and to get a more converged solution, you could decrease this number. If you want ZEUS to run faster and say, hey, I've found a converged solution more quickly, you can increase this number. Next we have the 2D option, where it's a character string, either yes or no. The default is no, so ZEUS assumes a 3D model. For 2D set to yes, then the Euler solver performs a two-dimensional flow computation. And for the 2D model input, the span-wise cuts have to be set to 2 for all of the C07 components. And then finally we have the wind tunnel wall flag, and this can be either yes or no. If the value is yes for wind tunnel wall, then the far field boundary condition of the global block of mesh is treated as the wall boundary condition to simulate the wind tunnel wall effects. By default, there's no wall at the far field boundary.